Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial topic in calculus. We'll be exploring the chain rule, which is an essential tool for differentiating composite functions. By the end of this video, you will be able to master the chain rule for nested functions and apply it to complex expressions, including those involving powers and trigonometric functions. Specifically, we will work through 3 challenging problems from the August 2017 exam paper, which will put your skills to the test. So grab your pens and paper and let's get started. Here's our first problem. We need to find the derivative of y equals the quantity x squared plus cosine squared of x, all raised to the power of 5. This is a perfect example of a composite function. We have an outer function, something raised to the 5th power, and an inner function, x squared plus cosine squared of x. The chain rule tells us how to handle this. It states that the derivative of an outer function with an inner function, g of x, is the derivative of the outer function, evaluated at g of x, multiplied by the derivative of the inner function. Let's apply this to our problem. We can think of the function as u to the power of 5, where u is equal to x squared plus cosine squared of x. First, we take the derivative of the outer function with respect to u, which is 5 times u to the power of 4. Substituting u back in, this gives us 5 times the quantity x squared plus cosine squared of x, all raised to the 4th power. Next, we need to multiply this by the derivative of the inner function. So we need to find the derivative of x squared plus cosine squared of x. Let's look at the derivative of the inner function. The derivative of x squared is 2x. That's straightforward. Now for the derivative of cosine squared of x. We must apply the chain rule again. Cosine squared of x is the same as cosine of x squared, so our inner function is cosine of x. The derivative of something squared is 2 times that something. And by the chain rule, we must multiply by the derivative of the inner function cosine of x. The derivative of cosine of x is negative sine of x. So the derivative of cosine squared of x is negative 2 cosine of x sine of x. Putting this all together, the derivative of the inner function, x squared plus cosine squared of x, is 2x minus 2 cosine of x sine of x. Now we just combine the results. The full derivative is 5 times the quantity x squared plus cosine squared of x to the power of 4, multiplied by the quantity 2x minus 2 cosine of x sine of x. The question stated that simplification is not required. So, we're done. We have successfully applied the chain rule to find our derivative. That first problem was a good warm-up. Now let's tackle our second problem, which is a bit more involved. For our second problem, we need to find the derivative of y equals the quantity x squared plus the quantity x squared plus 6 plus 2x squared, all raised to the power of 2, and then that entire thing is squared. Yes. Don't let the complexity intimidate you. The principle is the same. We just need to apply the chain rule multiple times, working our way from the outermost function to the innermost. First, let's differentiate the outermost part, which is something squared. The derivative is 2 times that something to the power of 1, multiplied by the derivative of the inner function. So we write 2 times the entire bracket, to the power of 1, and we multiply by the derivative of the content inside the large bracket. Now we need to differentiate the expression inside the large square brackets. This is a sum, so we can differentiate each term separately. The derivative of x squared is 2x. For the second term, we apply the chain rule again. Here we have another expression that is squared. The derivative is 2 times the content inside the curly braces, to the power of 1, times the derivative of that content. Are you ready for another layer? We need to differentiate the expression inside the curly braces. Again, it's a sum. The derivative of x squared is 2x. The derivative of the second term, 6 plus 2x squared, requires another application of the chain rule. This is our final differentiation step. The derivative of something squared is 2 times that something, to the power of 1, times the derivative of the innermost function, which is just 2. We've reached the innermost part and differentiated everything. Now we just need to assemble all the pieces. Let's work backward. The derivative of our innermost function was 2 times 6 plus 2x times 2. Plugging this into our next step up, we get that derivative inside the curly braces is 2x plus 2 times the quantity 6 plus 2x. Now, plugging that result into our next step, The derivative of the expression inside the curly braces squared becomes 2 times curly braces times that result. Finally, we substitute this into our very first expression for die dx. The result is 2 times the large bracket, multiplied by 2x plus 2 times the curly braces, times our final differentiation result. As with the last problem, simplification is not required. So, while you could expand this, the question asks us not to. This is our final answer. Fantastic work on that one. Now for our third and final problem. This one was actually featured in the August 2017 exam, making it a great example of what you might encounter. We need to find the derivative of y equals the square root of x plus the square root of x plus the square root of x. This is a nested radical expression. The first step to solving any problem involving roots is to rewrite them using fractional exponents. This makes them easier to handle with the power rule. So we start from the inside out. The innermost square root, the square root of x, becomes x to the 1/2 power. Next, the middle square root, which contains x plus x to the 1/2 power, becomes the quantity x plus x to the 1/2, all to the 1/2 power. Finally, the outermost square root contains the entire expression. So we rewrite y as the quantity x plus the quantity x plus x to the 1/2, all to the 1/2, all to the 1/2 power. Now that it's in a more workable form, we can apply the chain rule. Once again, we'll work from the outside in. The outermost function is something to the 1/2 power. Its derivative is 1/2 times that something to the negative 1/2 power, times the derivative of the inner function. This gives us 1/2 times the entire bracket to the negative 1/2, multiplied by the derivative of what's inside. Now we differentiate the inner function. It's a sum, so we differentiate each part. The derivative of x is simply 1. The derivative of the second term, the 1/2 power expression, requires the chain rule again. Here, the derivative is 1/2 times the inner part to the negative 1/2, times the derivative of that inner part. We're almost at the finish line. We just need to differentiate the innermost expression. The derivative of x is 1. The derivative of x to the 1/2 power is 1/2 x to the negative 1/2 power. Excellent. We've done all the necessary differentiations. Let's assemble our full answer by substituting back. The final result is 1/2 times the outer expression to the negative 1/2, all multiplied by the quantity 1 plus 1/2 times the middle expression to the negative 1/2, and finally, times the innermost derivative we found. This might look intimidating, but by taking it one step at a time and applying the chain rule consistently, we arrived at the correct answer. Let's quickly recap what we've accomplished today. We started with a solid foundation by reviewing the chain rule, our most powerful tool for composite functions. We saw how it allows us to break down complex problems into manageable steps. We then applied this rule to a series of increasingly difficult problems. First, we solved a problem involving a power and a trigonometric function. Then we tackled a heavily nested function, demonstrating the iterative application of the chain rule. And finally, we conquered a classic exam problem, transforming a nested radical into an exponential form to simplify the differentiation process. You are now well equipped to face similar differentiation challenges. The key is practice, patience, and the ability to recognize the structure of your functions. This lesson was brought to you by Math Zone African Motives. If you found this video helpful, please remember to like, share it with your classmates, and subscribe to our channel for more valuable lessons. Thank you for watching.